When an LLM finishes its training run, its knowledge solidifies into parametric memory, a static web of weights and biases locked inside its architecture. Because this memory is frozen, the model operates with a strict knowledge cutoff. It has zero visibility into proprietary enterprise data, internal databases, or secure documents. When a query demands information outside these weights, the system encounters a void. To resolve the prompt, the model defaults to pattern matching, fabricating a highly confident, mathematically probable, but entirely incorrect answer, a hallucination. High-stakes environments require a mechanism to dynamically inject ground truth facts into the model's awareness at the exact moment a user asks a question. The most intuitive solution is fine-tuning, sending the base model back to training to update its internal weights with proprietary data. However, this data reveals a significant operational hurdle. While updating a standard database remains a flat, predictable expense, continuously retraining an LLM to keep pace with changing data introduces skyrocketing compute costs and complex version management. There is a leaner, mathematically agile alternative, Retrieval-Augmented Generation, or RAG. RAG functions as a dynamic context engine. Instead of retraining the model, it fetches non-parametric memory, external data, at runtime, and feeds those specific facts into the LLM's context window. RAG represents a shift from static training to dynamic runtime injection, an approach designed to handle the high velocity of real-world enterprise data. The RAG pipeline begins with data ingestion. Before raw enterprise data can be mapped, it must be divided into manageable pieces. The naive approach is fixed-size chunking. Here, an algorithm blindly slices documents purely on a raw character count, for example, every 500 characters. This diagram shows the critical failure of that rigid slicing. By cutting at an arbitrary threshold, a functional logic loop or a complex legal sentence is often cut directly down the middle, destroying the actual meaning. To preserve context, the pipeline requires semantic chunking. Semantic and hierarchical chunking utilize boundary detection. They evaluate the document's structure, intelligently snapping around complete paragraphs and distinct functions to isolate intact ideas. The data must remain structurally and logically intact. Only then can the system attempt to translate human language into machine mathematics. Once the data is chunked, it passes through an embedding model. This operates as the core translation layer between human language and machine geometry. The embedding model converts a semantic chunk into a cascading array of decimal numbers, a vector. This array plots as a geometric coordinate within a multi-dimensional space. Because semantic similarity translates to geometric proximity, financial data points clump tightly together, isolated from HR policies. The efficacy of a RAG pipeline relies on the precision of this mathematical mapping. If the embedding model categorizes data poorly, the retrieval phase fails. With the data ingested and mapped, the pipeline shifts to runtime execution. This operation begins the exact millisecond a user submits a prompt. First, the query itself is passed through the exact same embedding model, generating a new vector coordinate. This coordinate is sent to a vector database, systems like Pinecone or ChromaDB. These are high-speed engines designed solely to calculate geometric distances between points. This diagram illustrates a similarity search. The database calculates the shortest distance between the new query vector and the stored document vectors, finding the top k nearest neighbors. During the synthesis phase, these geometrically closest chunks are routed into a hidden system prompt alongside the user's original query. Strict guardrails are applied here. The system explicitly instructs the LLM to generate an answer relying exclusively on the injected chunks. By treating the model purely as a reasoning engine over geometrically retrieved data, this pipeline successfully bypasses the LLM's parametric limitations. However, in production environments, the standard naive RAG approach frequently degrades. This diagram demonstrates the vector mismatch problem. A user's short question often possesses a completely different geometric signature than the dense, factual paragraph containing the answer, causing them to land geometrically distant from one another in the vector space. To solve this, engineers deploy topologies like HIDE, hypothetical document embeddings. HIDE bridges the gap by forcing the LLM to hallucinate a theoretical answer. It embeds that text, projecting a phantom point that lands directly next to the actual target data. Advanced RAG architectures require this manipulation of vector math to align user intent with the structural realities of the data. Naive RAG also suffers from blind synthesis. The system will retrieve and synthesize whatever chunks are geometrically closest, even if they are low quality or irrelevant. The ultimate evolution of the pipeline designed to solve this is known as agentic RAG. This diagram outlines an agentic RAG architecture. Instead of a linear pipeline, an LLM functions as a central orchestrator, dynamically routing pathways to a vector database, a Python interpreter, or an external web API. Within this loop sits a corrective evaluation step, or CRAG. The orchestrator mathematically scores the retrieved chunks against a confidence threshold before it generates an answer. If the chunks fail this quality gate, the agent invokes a fallback mechanism. It autonomously reformulates the query or routes out to a web search to gather better data. In an agentic loop, the LLM functions as an active data retrieval machine, autonomously refining its search until it clears its own internal quality gates. As upcoming models feature 1 million plus token context windows, a pervasive industry assumption suggests that engineers can simply dump entire databases into a prompt, rendering RAG obsolete. But forcing a model to process millions of tokens per query introduces extreme latency degradation. This comparative bar chart illustrates the compute economics at scale. Processing a 1 million token context per query incurs prohibitive costs, while targeted retrieval of only the top 5 chunks remains a fraction of the expense. Models also suffer from the lost-in-the-middle phenomenon. LLMs lose precision and reasoning power when the required signal is buried beneath an ocean of irrelevant noise.
Precision semantic retrieval is a permanent mathematical necessity for isolating signal from noise, regardless of how large context windows become. The bleeding edge of retrieval architectures is now moving towards graph RAG. While vector databases excel at semantic similarity, they struggle to understand explicit relationships across disparate, disconnected documents. This diagram shows a knowledge graph overlay. Graph RAG explicitly maps how entities relate to each other across the enterprise dataset, drawing logical connections between previously isolated chunks of information. The reliability of enterprise AI rests on the precision of dynamic routing, semantic chunking, and the underlying vector mathematics. AI engineering is increasingly a discipline of architecture, where the primary challenge is the design of smarter, agent-driven retrieval systems.